Hi, this is E637. I'm Charles Bouman, and today what we're going to do is we're going to pick up on the material on image coding, which is, I guess, basically the last section of the class that we're covering. And by the way, I should warn you, you have to do that last lab, which is the JPEG encoder. Have you guys started on that yet? Okay, good. That lab is more complex than some of the other ones. And you actually implement a true, standards compliant JPEG coder, which means there's a lot of little details, although we provide the header for you, which is helpful. And so you can get started on it early. Actually, one nice thing about that lab is it also helps you understand issues having to do with computer architecture and how you write algorithms to manage bits and thinking about all those sort of more hardware level operations that occur in a real computer that are often useful when you're actually processing images. So, we're going to talk about coding. So I guess I'll go to the slides. Coding. There's really two kinds of coding. So coding comes out of the field of information theory, which was basically a research area that was created by Claude Shannon. So he's sort of like the Albert Einstein of information processing, but not as well known. He basically recognized some very fundamental things. And we have a course, 642, which is information theory, which is an entire course dedicated to these topics. Roughly speaking, a lot of coding breaks into two major categories. One is source coding, and the other one is channel coding. And so in source coding, the idea is that you want to take some source of data and you want to code it so that you represent it with the fewest number of bits to the greatest accuracy. Okay. So this is what we'll really be talking about. But there's a whole other thing called channel coding. And channel coding is designed to correct errors in a communication channel. So a communication channel. Generally, communication channels are not perfect. So basically, source coding and channel coding both can be thought of in analog and digital forms. Although the output of source coding is digital, is always digital. I mean, in the end, you encode something as a binary file, and channel coding can be thought of as both analog and digital. So you can have an analog channel or you can have a digital channel. But in both cases, there's some capacity to the channels, which is the amount of information you can send across it with zero errors. So the big conceptual breakthrough with channel coding was that if you have a channel, the way people thought of channels before information theory was that you had a channel and there was some noise in the channel, like a AM modulation, right? So you send the signal over the AM modulation, and you receive it on the other end, and there's some noise. And the thinking was, the conventional wisdom was that, there's a certain amount of noise, and there's nothing you can do about it, right? And it's a function of the channel. And you can reduce the noise, but you just can't eliminate the noise. Well, this is kind of a conceptual breakthrough in channel coding, because what Shannon said was that you can compute the capacity of the channel if you model it as a random system, okay, and that it has a fixed capacity in terms of bits per second, and then you can get find a code which will achieve a rate which is arbitrarily close to that rate with no errors. or with asymptotically, with errors that asymptotically go to 0. So the idea, it's like, I don't know, this is maybe a terrible analogy, but I can't help myself. It's a little bit like superconducting materials, It's when the temperature gets below a certain temperature, it's not like the resistance goes to get very small. The resistance just goes to 0, okay? So channel coding is the basis of computers. Because when you have a computer, you don't think about it, well, I'm going to store the data into the file, and then when I read it, it's going to be close to what I stored. It's going to be exactly the same. At least that's the assumption. And when I send it over the Ethernet and it gets to the other computer, it's not like, well, it'll be close to what I sent. No, it'll be the same file. I mean, you don't even think of it as being changed, right? So this was a very fundamental change in perspective, the idea that somehow you can compensate for the noise in the channel and get a perfect output, or as close to perfect as you deem necessary. Okay, but the viewpoint, these two approaches, source coding. Well, they're not even approaches. These two problems, source coding and channel coding, are they're not exactly duals of each other, but they are kind of philosophically opposed, in a sense, you might say. Because in source coding, what you're doing is taking a bunch of data and you're squeezing it down to be more compact. But in channel coding, you take the same data and you expand it out. So you say, well, why would you do that? Well, because by expanding the data, you add redundancy, and the redundancy you add allows you to be able to recover from faults in the channel. But you say, well, why did you bother taking the redundancy out of the data in the first place? Well, because this redundancy is not optimal redundancy. What Shannon showed is that the joint source coding, the joint source channel coding theorem, is that you can achieve a result arbitrarily close to optimal by first taking the data sort of and freeze-drying it, like taking out all the excess liquids, right? And you get like freeze-dried coffee, okay? And then you, I don't know, well, I'm not exactly sure what the analogy would be here, but yeah, I'm really stuck, okay? But somehow you expand it a little bit to get it through the channel without any errors, and then you unfreeze-dry it on the other end. So the way it works is like this. Basically, you have your data source, x of n, right? And then the first thing you do is you do source coding, all right? And that produces an output which is reduces the number of bits. And then you do channel coding. Okay, and then this goes through a channel. And then this goes, and then you do channel decoding. And then you do a source decode. And finally you get the result. Now, if it's lossless coding, then this result exactly equals that. If it's lossy coding, then there's some distortion introduced, but the distortion is the minimum distortion given the bit rate of the channel. So the interesting thing is that by doing these modularly in two distinct steps, which don't talk to each other, so there's no joint optimization of these two things, you can get arbitrarily close to the optimal solution. So what the theorem tells you is that you don't have to worry about designing this all as one unit. You don't have to take so basically this can be like a JPEG image coder. The JPEG image coder doesn't need to know anything about the characteristics of the Ethernet channel. You just encode it, and then there's some sort of optimal channel encoding for the Ethernet channel, and it all works, okay? But now, in recent years, there's been interest in what they call joint source channel coding. There's some advantages to doing joint optimization of both of these things. but they're second-order advantages. Like, for instance, subject to some constraint like complexity or block length or something, you might be able to do a little bit better by merging these two steps together than you would by doing them separately. So that used to be a hot topic. I don't know if it still is or not, but it's interesting. Okay, so this compresses, this expands a little bit, but this compresses a lot more than that expands, and then the effect of the overall is to, or generally that's the case. I mean, I guess it doesn't really have to be. In any case, the channel coding achieves something arbitrarily close to a perfect channel, okay, but at the cost of reduced bit rate. So this channel would have some bit rate. It would have some bit rate it can achieve, but the problem is that there would be errors. And then by adding the channel coding, you reduce the errors. Okay, so so that's enough for channel coding, and now we'll just talk about source coding. This slide just says, well, you need source coding because digital images tend to be big. 6 megapixel isn't even that big anymore. I think you can easily buy digital SLRs with 24 megapixel. That's pretty common, and I'm sure they have higher resolution ones if you want to spend a lot of money. But the first digital camera we bought here at Purdue, okay, was the Kodak DCS 460C, okay? Has anybody ever heard of that? We still have it around somewhere. I should go get it. And it was based on a Nikon N90 camera body, okay? And N90, you haven't heard of it. Yeah, it was an old, analog film camera body, right? They basically ripped off the camera back, and they put and they had this big, the huge thing hanging down with the SCSI port on it. It was a big mess it had a hard drive in it and everything. Okay, it was sick. You guys laugh, okay? But this was cutting edge technology, okay? Someday you're going to get old, and everyone will laugh at what you do too, okay? So it was 6 megapixel, okay? So this was really hot stuff, okay? Okay, now how much do you think it cost? Thousands. Okay, give me a specific number. I'll accept bids.
4,000.
4,000. 30. Oops.
100,000.
Any more?
One.
It was 35,000 if I recall correctly. Yeah, we had to get an NSF grant to pay for it, I think. So that was your federal tax dollars at work, okay? And but man, that was a cool, state-of-the-art kind of camera, right? Now you can go and buy a 6 megapixel digital camera at Walmart for $75, right? So, what are you going to do? It was great fun, though. It was great fun showing up and be able to take pictures of the kids with the $35,000 camera. Anyway, so okay. Anyway, now so. Oh, yeah. So there are two kinds of source coding. Okay, so the moral of that story is just that cameras and video equipment take high resolution images, and there's a lot of data. So if you can do source coding of it, that's important, right? Could be if it's 24 megapixel and it's 3 bytes per pixel, you're talking about 75 megabytes per image, which is still significant, right? So there's two kinds of encoding. There's lossless encoding, and there's lossless source coding, and there's lossy source coding. Okay. So in lossless source coding, the idea is that you don't. This is also referred to as just entropy coding. So you just. This is a little counterintuitive. That you can take the data and just compress it down without losing anything. Okay. This is like, freeze drying. You take it, you squeeze it down. and then you reconstitute it, and it's exactly the same. It's like when you go on a camping trip and they have bacon and eggs, freeze-dried, whatever, but it really doesn't ever taste the same. That's really lossy source coding, right? Okay, because you lost something. But with data, you can take the file. If you take your Microsoft Word file and you use zip on it, you compress that down. Well, actually, modern Word files don't compress very well because they have entropy coding built into them now. But it used to be the Microsoft Word file was pretty large, and then you compress it, and it would compress quite a bit with zip. And when you unzipped it, it wasn't like, some of the words in your document had changed. It was exactly the same, right? Precisely. Every bit was exactly the same. So that's entropy coding. Now, the problem is if you use lossless coding on natural images, if you just take a TIFF file, TIFF actually stands for tagged image file format. So you can store all kinds of things in TIFF, but usually when for instance, you can put a TIFF wrapper around JPEG. But often when people say TIFF, they really just mean 24-bit, color, raster images. So it's uncompressed. That's often what they mean with TIFF. So if you try to do lossless encoding of a conventional raster color image, you won't get much compression typically. Of course, it depends upon the particular image, but a typical number would be maybe 2 or 3 to 1 maximum. So that's not enough savings for people to usually be satisfied. So that's where lossy coding comes in. If you're willing to have some distortion in the encoding, then the encoding can be the compression can be much better. And the reason is that let's say, for instance, in a medical image is an application where people often discuss the idea of lossless coding because they say, we don't want to lose any information because we don't want to take that chance. But if you have like a device which measures rather than 8 bits, let's say 16 bits per pixel, and if the last 4 bits are basically random noise, random noise doesn't compress very well. So that means that you really can't compress those last 4 bits at all. And even if you did a perfect job on the other, let me see, so 12 bits, you would still only get 4 to 1 compression. So lossless coding is particularly bad when you have a lot of bit depth and you have some noise, because noise just doesn't compress. So, so that brings us to lossy coding, and the idea there is you're willing to accept some degradation or some distortion, but maybe that's okay. In some cases, lossy compression can actually improve the quality of an image. For instance, if you have a very noisy image and you, do JPEG compression of it with, say, a wavelet coder like JPEG 2000, you can actually clip out some of the noise and actually remove some noise. It can look better after coding than it did before. So this is often a useful trade-off because you can get much higher compression ratios, and you may not lose any quality from the point of view of the customer, or the person who's receiving the data. So the visual quality may remain the same. There's also a thing called nearly lossless, where what can happen is that for some coders, a typical, we'll talk about this later, and you're doing this in the lab. When a typical coding application, you take x of ij is the image, right? And it first goes into a transform. So the transform takes the image and produces a decorrelated values, right? And then the next step, and we'll talk about this later, is an entropy coder. Oh, hold on for a second. I screwed up. Let me just redo this. I lied slightly. Okay, so the first thing you have is a transform. And the next step, I mean, this is sort of a canonical design for an image coder, a lossy image coder. You have quantization. Quantization is where the loss actually occurs. And then you have entropy coding. And then that is the coded version of the image. So I don't know, I'll call that y of ij, y. I'll just call it y, it's a vector, because it's no longer associated with pixels. And then when you want to decode, you take y and you put it in entropy code. And then you put it into inverse quantization. Now, inverse, you can't invert the quantization effects exactly, but you can approximately. So you associate each quantization value with its mean level would be a typical thing to do. That's what you do in a D to A converter, right? Because you don't really know what the signal coming into the A to D was. You just know it was in some range, and you output the value in the middle of that range, and then you take the inverse transform. And that's x hat of ij. So if you eliminate the quantization in the inverse quantization, so if you just entropy code the transformed image, then you get what's often called a nearly lossless. And the reason it's called nearly lossless is very often the transform isn't perfectly invertible. It's invertible mathematically, but it may not be invertible numerically on the computer to machine precision. So if you do a DCT and you take the inverse DCT, you won't get exactly the same thing back. It'll be plus or minus the least significant bit of the computation, or maybe a couple least significant bits of the computation in the floating point processor of the machine. So in that case, this and this are not exactly equal, but they're equal with plus or minus 1 or 2 bits, 1 or 2 quantization levels. So it's called nearly lossless. So lossless means that you get exactly the same thing out bit for bit as you put in. Lossy means that you have some quantization and then the output is not equal to the input, but you try to design it so that at a particular bit rate you get the best quality possible. And in lossy, you have quantization that occurs here. And then nearly lossless means that usually it means that you did no quantization, but you got something still that wasn't exactly bit for bit the same. It was just very close because the transforms are not exactly matched numerically by the computer in floating point precision. Okay, so now so we're now going to talk about entropy coders, or lossless coding. So lossless coding, in order to understand lossless coding, you first need to understand a concept called entropy. So a random variable, so let x be a random variable with the property that the probability that x equals I is equal to pi, right? And then in this case, the entropy of x is equal to the sum from over, here I'm assuming that without loss of generality, I is, well, without loss of much generality. It takes on values between 0 and m minus 1. So it's discrete. Now, if x is not a discrete random variable, so here I'm assuming that x is a discrete random variable with a finite number of possible values. It's also possible that it be a discrete random variable with an infinite number of values, but in that case it would always be countably infinite. And then the other possibility is that x is a continuously valued random variable. So entropy is only really well defined for discrete random variables. And so assuming it's discrete with a finite number of levels, then without loss of generality, I can just assume those levels are 0 through m minus 1. Because whatever they are, I can just map them to the m integers. Okay. So in this case, the entropy of the random variable is the sum from I equals 0 to m minus 1 of p sub I times the log base 2 of p sub I, right? So this is equal to, that's another way of thinking about it is this is the negative of the expectation, I'm sorry, I left the negative sign over here, of the log base 2 of p of x. So x here is a random variable which takes on values I. So this is the expectation. So if p of I is small, then its log will be very negative. So if I take the negative, the log will be very positive. So I guess the other way of looking at this is equal to the minus the or plus the expectation of the log base 2 of 1 over p of x. So if the probability is small, then the log is large, and you're looking at the expectation of that. So if, say, x only takes on one value, right, then it takes on that value with probability 1, and then the log of 1 is 0, so the entropy is 0. Entropy is a measure of how much uncertainty there is in the value of the random variable. The random variable can take on a lot of values and pretty much uniformly spread amongst those values, then the entropy is high. If it can only take on a few values and it's concentrated into just a few of the available values, then the entropy is low. Right? And entropy is measured in units of bits, typically, or nats. So this would be bits because I'm taking the log base 2. So if I have, let's see, so an example would be if I had, P, so if I had the probability that x, x equals I is equal to, say, 1 over m for I in the 0 through m minus 1 and 0 otherwise, right? So, so in this case, the entropy of x is equal to the log base 2 of m. It's the so if say if m is equal to say 2 to the b, so if there are 256 levels and the random variable is uniformly distributed between those, then it's going to be equal to just b. It's the number of bits it takes to represent the random variable's values. If they're not uniformly distributed, if they're more concentrated, then the entropy would go down. Any questions about this? Now, conditional entropy and mutual information is very important. So, you can define a concept of conditional entropy, which is the expected entropy of the conditional random variable of x given y. So if you know x, if you know y, you can ask, well, for a known value of y, what's the entropy of x? For two random variables, x and y. They're both discrete, say. And then what you can do is take the expectation over all values of y. And that's the conditional entropy. So it's the average amount of entropy that x has given knowledge of y. Right? So I'm taking the log of the conditional probability of x given y, and I'm taking the expectation over x and y. Well, I'm taking actually the negative log. So that's the entropy, and then the mutual information is, okay, the entropy of x given y will always be less than the entropy of x by itself. So knowing y can only tell you more information about x. If y tells you absolutely nothing at all, then the conditional entropy of x given y will be just it will just be the entropy of x. And in that case, the mutual information will be 0, because these will be identical, and you'll subtract them, you'll get 0. If, on the other hand, y tells you a lot about x, then the uncertainty in the values of x will be much smaller than they would have been otherwise, and this difference will be larger, and the mutual information will be large. So one thing that's kind of interesting is that if x is a random variable, and let's say it has some density function, p of x, right? So that the probability that x is a member of A is equal to the integral over A of p of x dx, right? So in this case, so this is just the density, right? So in this case, then, the entropy, so you can ask yourself, well, what's the entropy of x? Well, you'd be sort of tempted to say that it's equal to the integral, right, of, well, you might say it's minus the log base 2 of p of x times p of x dx, right? Just replace the sum with an integral. Unfortunately, this is not true. Okay? So, intuitively, it's unreasonable. So, if I have let's say that x is a Gaussian random variable with mean 0 and variance 1. Well, what's the entropy of that? So how many bits does it take to represent the value of x on average?
So it's continuous?
It's a continuous random variable. It's a Gaussian with mean 0 and variance 1. So if I'm going to encode the value of x, how many bits do I need?
As many as you want.
Well, I'm looking for a more specific word.
Infinity.
Infinity. Okay? You need an infinite number of bits, right? Because any place you cut off, you've gotten distortion in the representation. So continuous random variables typically have entropy which is infinite. Okay? So that's a problem because the entropy is infinite. But it's interesting. You can define a thing called the differential entropy. So, okay, I guess I'll do this like this. This is equal to, in fact, defined as this little h of x. Oh, I should make that uppercase x. All right. So this is called differential . So the differential entropy is defined like this, and it's interesting, but it doesn't have the same meaning as the entropy. But one thing that is interesting is that you can you can still say that if you have two continuously valued random variables x and y. So now let's assume these are not discrete. The mutual information is still defined as the differential entropy minus the conditional differential entropy. So, and the way to think about this is that if you take if you took x and y and you approximated the true continuous random variables x and y by discrete approximations, so you could quantize x and y and have a quantized version of x and y, and then in that case, once it's quantized, then the entropy is well defined. And if you take the limit as the quantization step size goes to 0, then it turns out that the entropy, this difference between the two entropies does converge to a limit that's well defined. So mutual information, so entropy is not well defined for continuous random variables. So instead you need to have a differential entropy concept. But mutual information is well defined for continuous random variables. And that's important because that allows you to do things like define the capacity of a channel or when the input and outputs of the channel are analog. So the information theory can be well defined in both the discrete and the continuous cases. Okay. All right. Now, let's see. Okay. So now we're going to talk about lossless coding of a sequence. So let's say we have a sequence of random variables xn. The random variables are discrete, and they take on values between 0 and n minus 1 with probability 1. So, and the random variables are independent and identically distributed. So I can define the distribution for one random variable, and then the random variable, the distribution of the product of the random variables is the product of the densities because we're assuming they're independent. Okay, so the distribution of x, the probability that xn equals m is going to be defined as p of m. Without loss of generality, I can assume that xn takes on values between 0 and n minus 1. Okay, so each xn you can think of as a symbol that you want to encode. We're going to do lossless encoding here, okay? So how do we represent xn with a minimum number of bits per symbol? Well, some of these xn's might occur very frequently, and others may occur very rarely. So how do you handle that? So, like for instance, let's say that xn had a binary encoding. So let's say that most of the time xn is so the probability the x. Okay, hold on. Let me give you an example. Let's say that the probability that xn equals 0 is equal to some reasonably large number. Let's say 1/2. Okay, so it's often equal to that, and the probability that xn is equal to 1 is equal to 1/2 minus epsilon, where epsilon is some very small number, and then we'll say, oh, but the probability that xn is equal to, I don't know, 1024, so that's a pretty big number, or 1023, I guess. Okay, that's power 2, is I should have just made it 1024. 1024 is equal to epsilon, right? So now what happens is you need 10 bits to represent it once in a great while. but most of the time you only need 1 bit to represent it. So if you're going to reliably always send this data without loss, you'd have to allocate 10 bits, but most of the time that would be wasted. So I guess if I made it 1023, then all the bits would be used. Okay, but any case, so how do you deal with this? Well, you only need to handle this case once in a great while. So the amount of information, the total amount of information represented by this is small because it only occurs once in a while. But when it does occur, you need more bits to represent it. So how do you do this? Okay, well, the first thing we're going to need is a code. So in a code, so we need a code. A code is a mapping from a discrete set of symbols 0 through m minus 1 to a finite binary sequences. So for each symbol m, there's a finite binary sequence sigma m associated with it. And for notational purposes, if I write the absolute value of sigma m, that denotes the length of the binary sequence, right? So in this case, the expected length of a binary sequence is the expected value of this expression right here, where m now takes on the value xn, because xn is the actual symbol you want to send, and x sub m here is the particular sequence of binary values you're going to send to encode each symbol. So n bar here is the expected number of bits per input symbol. So in the previous example I gave, 1024 is 10 bits, right? So using this, if I didn't encode this at all, I have to encode it. If I just did the dumbest possible encoding, where I just used 10 bits, and I just sent 10 bits per symbol, then n bar here would be 10, right? Okay. Now, so we can come up with more sophisticated methods, and for instance, Morse code. Everybody's familiar with Morse code, right? Mm-hmm. Okay. Okay. Who's not familiar with Morse code? You know, like Morse code is where you have the thing. Okay, I can't actually do it, but okay, Samuel Morse had a thing where you press on a switch, and then it would click on the other end, and this is how they would transmit signals from, say, New York to California. And it was revolutionary because before that you had to actually get a letter, write it out, put it in a satchel on a pony, and then ride all the way out to California. And of course, along the way, a lot of bad things could happen to you. So sometimes the letter didn't even get there. Okay, but if it did, it took a long time. Okay, so it was extraordinarily expensive. And then, this is why electrical engineers are so important, because we come up with ideas of how they can communicate real efficiently, and it completely changes society. And then afterwards, they don't give us any credit, but that's okay. Our reward is in knowing we did the right thing. Okay? All right. Anyway, so what we're going to do is in Morse code, they needed to encode like A through Z, right? So for each letter, they associated a sequence of dots and dashes. That's a binary code because a dot's like a 0 and a dash is a 1, right? So now, so that's like a code. So now for each entry, there's going to be a sequence. So say 0 here, we're going to make the first, well, we'll have the symbols 0 through 3. So 0 goes to 0, 1, 1 goes to 1, 0, 2 goes to 0, 3 goes to 1, 0, 0, 1, 0, 0. I'm just making this up, okay? So in this case, just as an example, the binary the word length in this case is 2, 2, 1, and 6, okay? So now, then this is how you would encode a particular symbol stream. So you have the 0 goes to 0, 1, the 2 goes to 0, the 1 goes to 1, 0, the 3 goes to 1, 0, 0, 1, 0, 0, and the 2 goes to 0, right? So this is like the Captain Crunch decoder ring. So for each, when you got when you bought Captain Crunch when I was a kid, right? because your mother didn't want to get it because it's this really sugary cereal. So you bought it because you really wanted it, and because inside of it they had a decoder ring, okay? And inside the decoder ring would tell you how to like encode messages to your friends, okay? So that was really cool. If you've ever seen the movie The Christmas Story, that's in there too, okay? So now, so what happens is, okay, so it's basically, but you may have already noticed there's a problem. Because when you go to decode this, you're going to have problems. Because you come here and you say, well, this could have been, let's see, this is, so even the symbol 3 here could be, if I take the symbol 3 goes to 1, 0, 0, 1, 0, 0. But who's to say I didn't really mean that this was, say, this could have been a 1, right? And then this could be a 2, and then this could be a 1 again, and then this could be a 2. So the symbol sequence 1, 2, 1, 2 would have the same encoding as the symbol sequence 3. So how can I tell those apart? How can I disambiguate between those two cases? So the answer is that, well, there's a problem, and to fix it, you need to make some constraints on your code. So let me give you, okay, so let me define some terminology. We say that it's a fixed length code if all the sequences of symbol sequences are the same length. It's a variable length code if they vary with the symbol, okay? So is Morse code a fixed length code? No, it's a variable length code. And if you think about it, what happens is that the most common symbols have shorter sequences. So for instance, I think, I don't know much Morse code, but I do know this, I'm almost certain, that E goes to dot, okay? Is that correct? Does anybody know Morse code here? Okay. I can say anything I want. Yeah. Okay, pretty much. But I'm pretty sure that E goes to dot, okay? So why do you think E goes to dot? Because E is the most common letter in standard English. So if you take an ensemble of standard English text and you count the frequency at which the different symbols occur, E is the most commonly used letter. So it goes to the shortest symbol, because whatever you do most often, you want to be easiest, right? Now, so that's the general strategy, that what you're going to do is try to map the commonly occurring symbols to short sequences. But you also have to reach other constraints. Each symbol sequence has to be different, and each binary sequence has to be different. Each code has to be different. But in addition, you have to have this problem that it's got to be decodable. Okay? So what are you going to do? Okay, so we say that the first thing we need is a definition. A code is uniquely decodable if there exists only a single unique decoding of each coded sequence. So we want it to be uniquely decodable. And one way of achieving a uniquely decodable sequence is to have what's called a prefix code. And a prefix code is perhaps a bad name for it, because a prefix code, it perhaps should be called a non-prefix code, because it means that a code is said to be a prefix code if any code is not a prefix for any other code. So this example I gave you is not a prefix code, and that's where you run into the trouble. It's not a prefix code because 1 is a prefix for 3. So the sequence 1, 0 occurs here for 3. So you have to make sure that every new code, one way of achieving a uniquely decodable sequence, and a way which is without loss of generality, includes, okay, you can show basically that a prefix code is not a serious restriction. It doesn't, there are things that are I think there are things that are non-prefix codes that are uniquely decodable, but they're not interesting. Okay, so you can achieve all interesting non-decodable codes are prefix codes without loss of any performance. Okay, so you can just assume everything's a prefix code, and this is not a prefix code. So you want to restrict yourself to prefix codes to make sure that you can uniquely decode the sequence. Okay. Okay. Now, this is an interesting result, which we'll come to I'm going to just mention it really fast. Okay, so there's a theorem which says that the expected code length is greater than or equal to the entropy, and we're going to show that there's a constructive way of finding a code which is within 1 bit of the entropy. Okay, and then we'll find a way of constructing a code which is asymptotically close to the entropy. So the entropy becomes the code length.